Okay, we'll begin. Are there questions? Okay, if not, let me start. So, was there a question? Okay, so let me remind you where we were. So, we are studying scalar perturbation. And we found altogether 6 gauge invariant variables. So, let me list them. So, these were phi b and psi b. Okay, these came purely from the metric. And then there are other variables which came from the stress tensor, combination of stress tensor and the metric. So these were the 6 gauge invariant variables if you don't make any further assumption, but then we made some assumption about the energy momentum tensor. So one is that we have this perfect fluid ansatz. Okay, so that, if you remember, that set all components sigma ij equal to 0, where sigma ij was the expression for Tij except for the trace part, okay, which went into the pressure. So the perfect fluid ansatz in particular gives sigma tilde equal to 0 because this is a scalar component of sigma ij. And then we saw that if we assume that the equation of state holds locally, okay, then namely there is local thermal equilibrium, then this gave P equal to 0. So that reduces the number of independent variables to 4. Okay. And now we are fine because now we have 4 equations which come from Einstein's equation. So let me remind you. So the Einstein's equation, if we write this as k mu nu equal to 0, okay, where k mu nu was r mu nu minus half r g mu nu minus 8 by g t mu nu. Then there are 4 scalars from here. Okay, so this had 4 scalars, okay, which came from k00, and then ki0 has 1 scalar because the gradient part is a scalar, 1 scalar, and kij has 2 scalars. Okay, one is a trace part, the other one is the double derivative del I del j of a scalar. Okay, so altogether 4 equations. So this gives you 4 equations. And the idea now is that we'll try to solve those 4 equations for these 4 variables. Okay. So we'll write down in momentum space. Okay, so we work in momentum space, namely with the Fourier Transform variables. Okay. But we'll drop the hats just for convenience. So when I write phi b, it should be understood that we are really talking about phi b hat because we are working in the momentum space. So let me write down those 4 equations, which in fact I had written down last time, but I'll write it again because today we are going to use it. So the first equation will be 3h psi b dot. And I forgot to tell that the initial condition will be provided by inflation at the horizon exit. Okay, but we will see to how we use it. Okay, H is always lambda dot over lambda. That's understood. Okay, and because sigma tilde is 0, this is 0. Okay, this is the perfect fluid condition. And the fourth one is zeta dot is minus H E O. So I'll first write down the general equation and then specialize to the case that we have. So this, because again P is 0, so this is minus pi. And the expression for pi also we had written down last time. This is so pi over H. This expression is what we had written. Pi over H is minus k square over so these all come from Einstein's equation. You have to basically work out the details, okay, but it's only linearized. So even though it looks complicated, it's not that hard. Okay, you have to basically expand the metric and keep terms to linear order in these variables. Okay, let me just check that I have it correct. Okay, so and other point I want to say at this stage is that whenever you talk about time derivative, we want to make, if we want to make it dimensionless, the natural scale is h. Okay. So h, which is the rate of expansion, has the dimension of inverse time. Okay. So zeta dot, for example, okay, the dimensionless quantity will be h inverse zeta dot. That sort of should be compared to zeta. And that's why I have written the expression for pi by h, right? Because h inverse zeta dot will be minus pi by h, and you see that that's related to zeta. Okay, so this is the quantity that's measuring the strength of pi by h essentially. So the first we'll analyze these equations for super horizon perturbation. So super horizon perturbation. These, as I have been emphasizing, are simpler. Okay, and we'll see also in terms of these equations that these are simpler. Okay. So super horizon perturbation, let me remind you, is k square is much less than lambda square h square. Okay. And the situation is simplest for those which remain super horizon all the way from T star to T last scattering. Okay, they from the horizon exit to last scattering surface. Okay, that, as we have been discussing, spans more than 2-degree angle in the sky. Okay, that's the separate kind of separation you're talking about. Okay. So super horizon perturbations means k square is much smaller than lambda square h square. Okay. And so we'll first analyze this case, okay, and we'll see that the equations simplify in this limit. So in particular, we see from this that pi by h is small. Okay, so in this case, pi by h is small. Okay, and we will set to 0 for approximation. In that case, zeta dot can be set equal to 0. Okay. So 4 now implies that zeta dot is 0 or nearly equal to 0 for super horizon perturbations, which means zeta is constant. 3 implies psi b equal to phi b. The other simple equation is if you take 1 plus 3h times this, sorry, you equate 1 with 3h times this. Let me write. So 1 minus 3h times 2. Okay, what does this give us? Okay. So this term cancels. Okay, you multiply by the 3h. Okay. This one, again, we can ignore for super horizon perturbation because it looks like it's k square plus lambda square. But again, when you actually scale it appropriately, right? For example, there is an h square sitting here, right? So you should really divide by h square to see whether this term is small or large, right? Here, there's an h sitting here, but there's psi b dot. So the dimensionless one object is 1 over h times psi b dot. Okay. So if you do that, if you divide by h square, then again, you can see that this term is small. So you can ignore this. Okay. So basically, that is saying that this should be equated to 3h times this. Okay. So this says that 4 pi g cancels. Okay, this h cancels. So del t rho bar is 3h, sorry, del t rho bar times zeta plus psi b is 3h rho bar plus p bar times r minus psi b. Is this clear? Are there questions? Okay, so let's try to simplify this. We have this equation, okay, energy conservation equation, del T of rho bar lambda cube is equal to 3 p bar lambda square lambda dot. Okay, so just expand it out. Okay, and you can easily convince yourself that this means del T rho bar. Okay, sorry, there's a minus sign. When you take del T rho bar times lambda cube, and then there is rho bar times 3 lambda square lambda dot. Okay, you take it to the other side. So this is minus 3 rho bar plus p bar. Okay. So del T rho bar is multiplied by lambda cube. This is multiplied by lambda square lambda dot. So when you take the ratio, it's lambda dot over lambda, which is nothing but h. Okay. So del T rho bar is really minus 3h times rho bar plus p bar. Okay. So this implies that zeta plus psi b is minus r plus psi b, or in other words, zeta equal to minus r. Okay. So the fact that zeta dot is 0, okay, implies that r dot is 0. So you see that even though the equations look complicated, when you consider super horizon perturbation, okay, the equations simplify, and you have already solved for 3 of the variables, right? Now r is the only variable to be found because zeta is expressed in terms of r. Okay. Well, okay, psi b and phi b, okay, we have to find psi b and phi b. Let's see, yeah. Okay, so we have to find psi b and phi b in terms of r. Okay. And then because r dot is 0, right? R at the last scattering surface will be the same as the R at horizon exit. Okay, so that's how we relate everything to the value of R at horizon exit. And the fluctuation of that you have calculated already by studying quantum fluctuations during inflation.
So the energy conservation that we have used,
Yes.
shouldn't that be the total energy, like rho bar plus rho tilde, p bar plus
Yeah,
p
yeah, but we are working to first order, right? In perturbation. So here everything is already has a one factor of perturbation, right?
Yeah.
So it will give corrections of order second order in perturbation. Okay, so whatever correction you are suggesting to this equation, will multiply this zeta plus psi b, right, and it will become second order in perturbation. So this is all linear perturbation, and the reason that is valid is because we know that the at the time of last scattering, the perturbations are small, like 1 in 10 to the 5. Okay, and they remain small all the way from the horizon exit to the time of last scattering.
Okay.
Any other question?
So it might not be relevant, but I mean, is there a reason why these equations are first order in time?
These equations are,
First order in time derivative?
yeah, basically, okay, we have combined things to make them into first order because let's say because we have seen, for example, the Friedman equation, right? If you think of Friedman equation plus the energy conservation, they are both first order in time, right? And we have seen that for the background, we can reformulate Einstein's equation as a pair of first order equations. And
Okay.
basically, we do the manipulations in the same way here. That we have some second order equation, okay, but we can combine them with other equations. For Einstein's equations also, right, we started with a second order equation, right, because there's an a lambda double dot, if you remember, or a double dot. But then we showed that it's possible to combine that the other equations to make the whole thing instead of first order equations. And that's exactly the same thing we are doing here.
Okay, yeah.
Any other question? Okay. So now the idea is that we have already psi b equal to phi b. Okay. So we are going to substitute here. Right? We just set psi b equal to phi b. Okay. R is constant. Okay. These are background values, and see if we can solve them. Okay. So the second equation is the only one that we are going to use, but I'll first also write down all these simple results that we have already found. So we have zeta equal to minus r, zeta dot equal to 0, which means r dot equal to 0, and psi b equal to phi b. Now let's look at 2, which gives phi b dot plus 3h phi b dot phi b. Okay, I have just set psi b equal to phi b. Sorry, not 3h, h phi b. I think I have written h phi b, right? Yeah, h phi b. Equal to 4 pi g rho bar plus p bar over h times r minus phi b. Okay, now let's consider the period when we are inside a given era. Okay, which means that only one component dominates, only one component of T mu dominates. Okay, which could be matter, radiation, or energy, or cosmological constant. Okay. So in this case, we can write the equation of state as P bar equal to W rho bar, where W, for example, is 0 for matter. It's 1/3 for radiation, and -1 for cosmological constant. So if you substitute it here, and now let's bring the phi b on the other side, we get an equation phi b dot plus h phi b plus 4 pi g rho bar plus p bar. Okay, let me write it as 4 pi g h. I'm going to multiply by h over, sorry, this I want to write as w plus 1 into rho bar. And here you have h square, right? Because I have multiplied by h in the numerator. But what is h square? H square is 8 pi g over 3 times rho bar. So on the right hand side, you have 4 pi gh again, and rho bar times 1 plus w over h square. Okay, but h square again I write 8 pi g over 3 times rho bar. Is this clear so far? So there is a 5b here. So what I did was that I brought this on the other side and then use this equation of state p bar equal to w rho bar, right? So write it as w plus 1 times rho bar. And then here I know the expression for h square, which is a simple expression. So I multiplied by h on the top and h on the bottom. So h square I replace by 8 pi g over 3 times rho bar. So this can now be written as phi b dot plus h phi b times 1 plus, here you see that this is 3 in the top, so 3 times w plus 1 over 2 equal to, here 3 times w plus 1 over 2 times r. Is this clear? Now from here we can already see that if we can argue that phi b dot is 0, then there is a simple relation between phi b and r. Right? Phi b is just proportional to r, and you can calculate the constant. There is also a h here. H. Right? Because this h. The 4 pi g cancelled with the 8 pi g, so give you 2 in the denominator, but the h is then. Okay. So if phi b dot is 0, then there is a simple relation between phi b and r. Right? And now we'll see that phi b dot indeed approaches 0 well into the a given era. Okay, other questions? So let me write this in a somewhat neat form. So phi b dot plus this one I'll write as 3w plus 5 over 2. 3w plus 5 over 2 h phi b equal to 3 times w plus 1 over 2 hr. Okay, I'm going to write this, copy this again in the next page because we will solve this. So we have phi b dot plus 3w plus 5 over 2 phi b. Okay, let me put the h inverse here. Equal to 3 times 1 plus w by 2 r. Okay, r is constant. Okay, that we have already found. Now, we'll be really interested in the matter and radiation dominant area. Okay, because you want to find the relation between phi b and r at late time. So in matter or radiation dominant area, Okay, this the conclusion that I'm going to draw will be valid also for the cosmological constant dominated era, but let's just focus on matter and radiation dominated. Okay, but before I do that, maybe I can just say in words what's going to happen. Okay. So you can see that this equation, okay, if you put the H here, okay, if you put the H here, this equation, okay, is the equation of a particle traveling with friction under a constant force, okay, under a constant force. Okay. So phi b you can think of as the velocity of the particle. Okay. So phi b dot is the second derivative of the velocity. Okay. The second term, okay, is something proportional to the velocity. Okay, it's acting in the opposite direction because there is a plus sign over here, so it's like a friction. And this is like the constant force that is applied to the particle. Now you know that in such cases, if there is a friction, then the particle eventually reaches a terminal velocity. When it reaches the terminal velocity, the phi b dot will go to 0, and the value of the terminal velocity will simply be given by solving this equation, right? So phi b will be 3 times 1 plus w over 3w plus 5. So this is the physics. You have to see it in terms of solution of differential equation. Okay, so this is, so we expect that in any given era, okay, as time progresses, phi b will approach this particular multiple of r. But let's see this in some explicit details. So in matter and radiation dominated era, H goes as some constant over T plus C. Okay, so K and C are constants. Okay, if you remember, because lambda goes as some power of T, right? T to some alpha. So lambda dot over lambda goes as 1 over T. Okay, and I have just added this constant because the origin could be different in different era. So if we now substitute here, okay, we get T plus C over K times phi b dot plus 3w plus 5 over 2 phi b equal to 3 1 plus w by 2 r. Okay, and now I'm going to just rewrite this as T plus C phi b dot as some constant plus a phi b equal to br, where a is basically 3w plus 5 over 2 times k, and b is 3 times 1 plus w over 2 times k. Okay. So this equation you can easily solve. Okay, so you basically multiply by T plus C to the power a minus 1. So this gives you T plus C to the a times phi b dot. This gives you a T plus C to the a minus 1 times phi b. Okay. So that net result is d dt of T plus C to the power a times phi b. So this is equal to b times r times T plus C to the power a. Okay. So just integrate once. So C T plus C to the power a phi b will be b over a times r. What did I do here? This should have been a minus 1. Okay, because I multiply by T plus C to the a minus 1. T plus C to the power a. Remember that r is constant, right? So when you take the derivative of this, it only acts on this, right? So that a cancels this and you get T plus C to the a minus 1. So plus a constant, of course, that's constant of integration. And so this tells us that phi b is b over a times r plus d over T plus C to the power a. But now as T becomes large, okay, within the given era, it goes to b over a times r, but b over a is here 3 times 1 plus w over 3w plus 5 times r. Is this clear? So even though this formula was derived for assuming that h goes as k over t plus c, this in fact is also valid for w equal to -1. So for w equal to -1, you have already seen that phi b is 0, right? We have to actually solve the equations for cosmological constant dominant era, that's during inflation. So for w equal to -1, phi b is 0. For w equal to 1/3, you can work out what this is, right? Say 3 plus 3w will be, this is 7 over, this is 7 over, no, sorry, 7 over 4. W equal to 1/3 will give you 4 over 5. 4 over 5?
6.
4 over 6. Okay, so it will give you 2/3. And for w equal to 0, we get 3/5. So what this is saying is that in inflationary phase, phi b is 0. Once the universe becomes radiation dominated, phi b starts changing, and quickly it approaches the value. What did we find? 4 over 6, 2/3 r. Then when it changes, the universe changes from radiation to matter dominated. Again, phi b starts changing, and it settles down to the value of 3/5 r. So if you plot phi b versus, right, if you plot phi b versus t, it goes like, it starts at 0, then it settles down to, this was 2/3, and 2/3 is larger than 3/5, so it, and it settles down, which is 3/5. Okay, so that's the way phi b changes. But we want to determine phi b at the time of last scattering, because everything we are trying to do at the time of last scattering. So let me write this formula again, and then we'll see what we want to do. So phi b is 3 times 1 plus w over 5 plus 3w, right? R. Yeah, 5 plus 3w. So this, at the time of last scattering, at t equal to TLS, there you have already seen universe has become matter dominated, so W is 0. So this becomes 3/5 r. So this basically determines all the fluctuations at the time of last scattering in terms of the value of R at the horizon exit, because R at the time of last scattering is the same as R at horizon exit. So at t equal to TLS, what we find is that phi b and psi b, those are equal, are given by 3 over 5 Ri. R is given by Ri, and zeta is given by minus Ri, because zeta is minus R. Is this clear? So now any 2-point function, okay, so 2 quantities, it could be phi b or psi b or R or whatever at the time of last scattering, will be given in terms of, determined from, because there may be some multiplicative factors. at t equal to t star. Is this clear? And this we have already calculated, right, for inflation. Calculated. Okay, of course, for a given model of inflation, right? Given model of slow roll inflation. And these quantities can be translated to temperature fluctuation. Okay, it still requires some work, okay, because you have to understand how temperature is affected by these various quantities. But you can already see, for example, that what is phi b? Okay, if you remember, in the E equal to B equal to 0 gauge, B equal to 0 gauge, phi b is phi, right? Okay, and what was phi? Okay, phi was the coefficient of minus dt square in the expansion of the 1 plus 2 phi, in the expansion of the metric. So that means in this gauge, okay, this gauge basically sets the diagonal off diagonal components to 0, okay, and some part of the diagonal to 0. So in this gauge, what we find is that the phi b, okay, translates to phi, and that's a fluctuation in the 0, 0 component of the metric. But 0, 0 component of the metric, of course, will affect the frequency of the photon that emerges from that point, or equivalently the temperature, apparent temperature of that photon by redshift. Right? If the gravitational potential is large or large in magnitude, say, okay, it's a negative normally in a massive object. If it's large in magnitude, then there will be larger redshift. So these fluctuations, okay, these are the gauge invariant quantities. So any observable, okay, like temperature fluctuation, can be translated to fluctuations of these objects. Phi b, psi b, r, and theta. Okay, that's not the whole story, because we'll also have the tensor fluctuations which we'll analyze. But once you understand all the fluctuations of the metric and the energy momentum tensor, all observables in principle can be computed in terms of those. Okay, and this we'll discuss later in some detail how to do this. Are there questions? Okay, so if there are no questions, we'll proceed with the other perturbations. Okay, the vector perturbation and the tensor perturbation. And again, we'll work in the super horizon scale first. Okay, I should have emphasized maybe here that these formulae that we derived is valid for those perturbations which remain super horizon all the way up to last scattering surface. Because as we have discussed, that if the perturbation becomes sub horizon, okay, before it reaches the last scattering time, then the equations change. And you have already seen, in fact, in terms of these equations themselves, right, that there are effects which you have ignored, okay, the effects involving these k-square factors, okay, which will become important, okay, once the perturbation becomes sub-horizon. Right? In that case, this one will be large instead of being small, right? Because k-square will now be much larger than lambda square h square. Okay? So those effects we will have to analyze separately afterwards. Okay, right now we are just dealing with super horizon scales. Okay, so now let's consider vector perturbation. So here let me remind you that we had altogether 4 vectors, of which 2 came from the metric and 2 from energy momentum tensor. So let me remind you how it entered the metric. So metric, I'll only write the vector part, dt square minus 2 lambda of t dxi dt times si. Okay, remember we had written as plus 2 lambda dxi dt times bi, but then bi will decompose into minus to del I b minus si. Okay, so that's where the si entered. And then inside dxi dxj there is one factor, so plus dxi dxj. Okay, it had a delta ij plus del I think we called it fj plus del j fi. And of course, these all satisfy this divergenceless condition. So this is 0 and del I fi equal to 0. Yeah, or if you are working in momentum space, then this is k dot s equal to 0 and k dot f equal to 0. And from the energy momentum tensor, also we had 2. So Ti0, this had a q tilde I, okay, which you decompose into a scalar, that is del I q tilde plus capital Qi. So I only write down the vector part. And then we had Tij, okay, when you label, okay, it had this sigma ij, which had a vector part, del I sigma j plus del j sigma I. And again, we impose these divergenceless conditions. Sorry, del I sigma. So you have 4 vectors, one gauge transformation, gauge parameter. Okay, so we have one gauge parameter, which is a vector, and that is the xi I. Okay, so xi I again we decompose into a scalar part, which is a gradient, and then the transverse vector. But so the upshot is that we have 4 vectors and one gauge parameter. So you should have 3 gauge invariant quantities. So the gauge invariant quantities from the energy momentum tensor, both of these are gauge invariant, Qi, sigma I. And then we had a combination of S and F, which was gauge invariant. That was Fi dot plus Si over lambda. Okay, so these are the 3 gauge invariant quantities. The perfect fluid condition on such set sigma equal to 0. In fact, it said the whole of sigma ij equal to 0. So remember, right? Tij only the trace part was non-zero. Okay, so in particular, set sigma equal to 0. So that reduces to 2 gauge invariant quantities. And now Einstein's equation has 2 vector components. So one of them from Ki0, the other one from Kij. Right? Because Kij has a component which is the del I kj plus del j ki, right? So that gives you 1, and this has 1 component. So you again expect 2 equations in 2 gauge invariant variables, so we are fine, right? We have 2 equations for 2 variables. And what I'm going to do now is to write down those equations in the next slide. Are there questions?
So after using the gauge parameter, we had 4 vectors, right?
No, I think after using the gauge parameter, we had 3. Because you can see, right? Tensors have normally 2 parameters, right? Because tensors have 2 vectors, one from the I0 component, the other one from the IJ component.
Yeah.
You expect 2 from the metric, 2 from the energy momentum tensor. That's 4 vectors altogether. And we have one gauge parameter. Right? The xi goes to xi minus ii. That's a vector gauge parameter. Right? Once you impose the del I ii equal to 0 condition. So we had 4 variables before counting gauge transformation.
Okay.
Yeah, if you go back and see the counting,
Yeah.
right, we have really 3 gauge invariant quantities, right? That's what these are. This reduces it to 2, and then Einstein's equation gives you two equations, okay, Ki0 and Kij.
Yeah.
Okay, thank you. So let me write down the equations. So I'll leave as an exercise to check that the equations one is Qi dot plus 3hqi equal to k square sigma I, but sigma I is 0 by the perfect fluid answer, so this is 0. And the other one is k square times fi dot plus si by lambda equal to 16 pi gqi. Okay, so once you determine qi, okay, this will be automatically determined. So let's try to determine qi from here. Okay, and that in fact is easy to solve. So this one gives you a solution that qi at t is qi at t star horizon exit times exponential integral minus t star to t dt prime over 3 h of t prime dt prime. Okay, this is a first order differential equation. There is a simple solution. H is a function of t, of course. Now qi of t star is 0, right? We had calculated the fluctuations and we didn't find any. But what this is saying that even if qi of t star is non-zero, qi of t approaches 0, it's exponentially damped as long as you are in the cosmological constant dominated era, okay, because h is constant. Then once you exit into radiation or matter dominated era, right, h goes as 1 over t. So this integral dt prime 1 over t prime is logarithmic, right, with some coefficient. So then qi of t will fall off as power law in t. Because that even if qi of t star was non-zero, it will first fall off exponentially, okay, and then as power law. So this basically says that the qi of t goes to 0 at large time. Okay, large time means our last scattering is large enough, okay, compared to the time scale that we are talking about. And once qi of t approaches 0, then the other gauge invariant quantity also becomes 0. Also becomes 0. Okay. So net upshot of this, okay, is that there is no vector perturbation. Okay, so at the time of last scattering, we can just set all the vector perturbations to 0. Are there questions? So now let's look at tensor perturbation. Okay, that's the last remaining thing to do. So the gauge invariant variables here are HT Ij and sigma T Ij. Okay, with all the transverse conditions, right? The trace is zero, the derivative, the divergence is zero, and so on, right? You'll be working momentum space again. So divergence zero means Ki Hij equal to zero and Ki sigma T Ij. And now again we use the perfect fluid ansatz. This set sigma Tij to zero, right? That we have already seen. The whole of sigma Ij set equal to zero. So basically the Einstein's equation is force free. Okay, there is only one tensor component of the Einstein's equation that comes from the Ij component, and that has no source. Okay, so basically Rij minus half Rgij equal to zero is what we have to solve. So to simplify this, we can just expand H in a basis. To choose a basis. Okay, in fact, we can choose the same basis that we chose for calculating fluctuations during inflation. So ES of K for S equal to 1, 2. Okay, satisfying all the conditions, namely Ki ESIJ equal to 0, ESII equal to 0, right? The trace, etc. Okay, so there are two independent basis vectors of this kind. And then you can expand H Tij as sum over S equal to 1 to 2 HS. These are all functions of K and T. Here I'll write explicitly K and T times ES Ij of K. So basically, these are the dynamical variables for which you have to write the equations, right? These are just fixed choice of basis polarizations. And now, again, I'll leave it as an exercise. That Einstein's equation Kij equal to 0, okay, or the transverse part, the traceless transverse part of K equal to 0. This gives, okay, so once substitute, you can equate coefficient of each ES to 0 because they are independent basis vectors. So you get del T square HS plus 3H del THS plus K square HS. Okay. And now we are going to Hershey's question about why we didn't get second time derivative. Okay. Physically, basically, the absence of second time derivative is showing that the only degrees of freedom which are dynamical, okay, are really the tensor degrees of freedom. Right? Here you do see that there is a second time derivative. Right? This you cannot eliminate because after all, I mean, in flat space you should get gravitational waves. So indeed there is a second time derivative, but this appears only for the tensor component. Okay, others are non-dynamical. Okay, that's why you have first order equation there. Okay, is this clear? I think I forgot a lambda square. Yeah, this is K square by lambda square because it's always scaled, right? This is a co-moving momentum, so the physical it will always depend on this because this is a physical moment. And again, we see that once you divide by h squared, right, because this is time derivative, second order time derivative, once you divide by h squared, okay, to make this dimensionless, then you get the combination k square over lambda square h square, which is small. So for the super horizon perturbation, k square over lambda square h square small, the equation takes the form del t square hs plus 3h del t hs equal to 0. And this has a solution for del t hs. So this is del t hs is del t hs at the horizon exit times exponential of minus 3 integral t star to t dt prime h of t prime. Now, at the horizon exit, you have seen that hs approaches a constant, right? And so this is 0. And this tells us that del t hs is 0 for all time. Okay, so this implies that hs is constant. And hence, hs at t is basically hs at t star. So once you have calculated tensor fluctuation at t star, you can that automatically gives the tensor fluctuation at the time of last scattering. Again, this is for the super horizon perturbations, right? For sub horizon, this term will play an important role. Other questions? So let me write it again. So you have hs of TLS equal to hs of T star. So now if you want to calculate, for example, hs of K TLS hs prime of K prime TLS, this is exactly the same as what we had calculated at the time of horizon exit, namely hs of K T star hs prime of K prime T star. So the net conclusion then is that all fluctuations at the time of last scattering are determined from two quantities. One is R K T star, R K prime T star, and HS K T star, HS K prime T star. Is this clear? Are there questions? So these are calculated during inflation. So next one, which I'm not going to start today, but I'll discuss what we are going to do roughly. That we want to try to relate to observations. Okay? We relate to observations. Okay? But first we'll do the analysis in general. So let's suppose that chi is some observable. Is some observable. Okay, whose fluctuations we can observe. Okay. So chi could be, for example, temperature fluctuation. Chi could be delta T. Okay, the Fourier transform. So what you observe is of course not delta T. It doesn't make sense to talk about delta T in one direction, but you calculate delta T at two different points and observe the expectation value, okay, which means that you keep changing the origin, okay, keeping the separation fixed, and see how the fluctuation, what kind of average you get. Okay, and this is what you are going to try to make more precise. So in general, we expect, chi kt to have the form of fk times r k at t star is TLS for scalar perturbation. Or related to some gk times say hs kt star for vector perturbation. Sorry, vector tensor fluctuation. Okay, if the quantity whose fluctuation you are considering is tensorial, then so what are these fk and gk? So fk is some function of k. Typically, if the perturbation is super horizon, then fk should be simple to calculate, because the fluctuations of r at the of all the scalar variables at the time of last scattering has simple relation with ri, with r at t star, and so fk will expect it to be simple. Okay, so it should be simple for super horizon. But it can be complicated. For sub-horizon scales. Because at the sub-horizon scale, you have to take into account these effects, okay? In particular of the k-square terms that you have ignored. Okay? And that means that the r, okay, or all other variables, phi b, psi b, etc., okay, at the time of last scattering, okay, we can still evolve by linear perturbation. Okay, it's a linear equation. But in general, the relationship between the values of these quantities at the time of last scattering, okay, to the value at the horizon exit will be more complicated. Okay, because the evolution equations are more complicated. And once you have gotten these quantities at the time of last scattering, okay, then of course we have to also figure out how to translate to something that you observed like temperature. But that part is reasonably easy to analyze using physical considerations, because as I said, for example, that the fluctuation in the gravitational potential will automatically give rise to redshift and transit to temperature fluctuation. Right? So similarly, you have to see what the other fluctuations can do, right? Which ones can actually cause fluctuation in temperature. And for the linear perturbation, you just at the end have to add other contributions, right, to these various fluctuations. So this will be one thing that we want to analyze. We'll try to analyze the f of k, okay, and also g of k. That both for super horizon scale, in which it's supposed to be simple, but also for the sub horizon scale, right? Because we will see that a lot of the data refers to sub horizon scale fluctuations, and there are interesting patterns over there that we'll find. But the second point you have to analyze, okay, and in fact that's what we'll probably do first, is the following: that what we observe in CMB is angular correlation, not spatial correlation. Namely, we look at the last scattering surface and we calculate the 2-point function between points that are separated by some angle. Now it's clear that this should be related to the spatial correlation function, because after all, if we know the spatial correlation function, we should be able to reconstruct these angular ones, but it will require some effort. So we need to make an effort to convert k dependence, okay, or mod k omega dependence of Ri kt. Okay, whatever I am saying is also valid for the tensors, but let me just write in terms of R. To angular correlations. Okay, in fact, we will see that just like instead of spatial correlation, we have here considered in momentum space is a Fourier transform of the spatial correlations. Similarly, the angular fluctuations are usually encoded in the angular momentum space. So we do a kind of Legendre transform and write it as a function of L, right? Instead of writing in terms of K, we write in terms of L. Okay, and the idea is that knowing this, you should be able to figure out, okay, the distribution in the L space, but it will require some effort to make this translation, right? How to go from here, which you know how to calculate, to here, which you know how to measure. So that will be one more thing we have to do. So I think today I'm not going to start a new topic. Okay, so I think I'll end here. So next time, that is tomorrow, we'll try to first analyze how to convert from the spatial correlations to angular correlation.
Sir, is there any reason behind we observe angular correlation in CNP?
Well, because
Or-
that's what we see, right? I mean, we are sitting at one particular point in the universe, right? And so when you look at the CMB, we see the CMB radiation coming from different directions, right? And we really have no choice but to observe at various angles on the CMB at the time of last scattering surface, right? So you cannot observe CMB produced elsewhere because they are not reaching us today, right? So because you can only observe the ones that are reaching us.
Okay, sir.
And that's why what you observe directly is the angular correlation, right? If we could do an experiment in different parts of the universe, right, in widely different parts, then you may be able to directly also observe the spatial correlation, but that's not what we are doing, right? We are sitting in on the Earth and then observing CMB coming from different directions.
Okay, sir.
Any other question?
Sir,
Yes, go ahead, please.
Measurement wise, like, are we measuring correlation between 2 points on the circumference at the last scattering surface, or like not circumference at the surface, or are we sort of drawing a like the analog of an arc and averaging the data there?
Yeah. So what you are doing is that you are basically, we'll see how to convert this into the angular momentum space. I think it will become clear. So what you observe is chi theta phi, chi theta prime phi prime. Right? Now, which basically means, of course, the origin you can fix, and then you average over different choice of the origin. See, this will depend only on the, when the average means that you are averaging over different origins, right? So at any given point, right, let's take this. Okay, so what you really do is you fix a point and take another point at an angle theta, okay, arc length theta, and you calculate the product of chi here. Then you do the same thing. Okay, you pick another point, say here, and equal distance. Okay, again theta. Okay, you calculate the product of chi here and chi here. That is delta t here and delta t here, and then you average over the whole sky. That's what you measure. Because this expectation value, right, from the quantum mechanical viewpoint, this expectation value should have been that you work at a fixed angle, but you average over many copies of the universe. But of course, you don't have many copies of the universe, right? So the best we can do is to do the averaging by simply shifting the origin and doing this averaging. Is this clear?
Yeah, I'm not sure I'm able to understand what does this imply.
What does this imply?
I mean, so we are keeping the theta minus theta prime, phi minus phi prime sort of fixed. Well, not that, but the arc.
We are keeping the arc length fixed, right? In theta phi,
Yeah,
theta
the
prime.
arc length fixed. So some relation between theta and theta prime and phi prime.
Exactly. Yeah.
And then we are varying, let's say, theta and finding theta prime, phi prime accordingly.
Yes.
And taking that correlation and averaging over all values of theta and phi.
Exactly.
But what does that mean for the temperature? Like, what are we measuring? I'm still not able to.
The temperature, right? Delta T. We look at a given direction in sky, right? You calculate how much the temperature varies from the average CMB temperature. So that's delta T at some angle, okay? And you calculate delta T at theta prime phi prime. Take the product, okay? That's a number, right? Then you change your theta phi and choose theta prime phi prime accordingly so that the arc length remains the same. You calculate the product again. And then you average over many choices of the theta and phi.
Okay.
Right? So that's what you do. Calculation wise, that's what you calculate. But as I said, ultimately the way to express this is not in terms of the angles, but in terms of the Legendre transform, right? In the L space, in the angular momentum space, right? And we will see how to do that. But the measurement wise, this is what we are doing.
Well, when we said that there is a scale invariance in the spectrum,
Yes.
what does that imply for this correlation?
We'll see. We'll relate this to this, right? And then we'll see what scale invariance means for this.
Okay.
But scale invariance, right? The way the scale invariance was originally derived, this Harrison-Elizabeth spectrum, right? That was not for this, okay? Because that was not meant for. Well, it was. You can say it was meant for microwave background also, but that was for the structure formation, the kind of structure we see in the universe, right? So that directly referred to the spatial correlations. And there we explain what scale invariance means, right? Basically, it has to go as 1 over omega cube.
Yeah, okay.
And that will translate to some property of this. Okay, when you convert this to the L space, for example, okay, you will get some function of L. and it will imply some particular property of f of L. Okay, how it should change as a function of L.
All right.
Any other question? Okay, if not, we'll stop here and we'll continue tomorrow.